automatic systems can detect aircraft fires or potential ignition which might not be apparent to the crew until they have developed to an extent which makes their successful control difficult or impossible. These systems are based upon both heat and smoke sensing. Smoke detection is used in toilet compartments, avionic base, and cargo holds. Normally, alert or caution are activated locally for toilet smoke detectors for cabin crew investigation, though in some types a toilet detector can trigger a fire warning on the flight deck. All other fire and smoke detector alerts and caution are normally enunciated in the flight deck. In every case, it is important that crew members understand exactly what type of detection system is being used, in which location in their aircraft, and exactly what is being detected. Only with that understanding will be able to know exactly what any warning system is telling them.
Smoke detectors. A smoke detection system monitors the laboratories and cargo baggage compartment for the presence of smoke, which is indicative of a fire condition. Smoke detection instruments that collect air from sampling are mounted in the compartment in a strategic location. A smoke detection system is used where the type of fire anticipated is expected to generate a substantial amount of smoke before temperature changes. It is efficient to actuate a heat detection system. Two common types used are light refraction and ionization. Light refraction type. The light refraction type of smoke detector contains a photoelectric cell that detects light refracted by smoke particles. Smoke particles refract light to the photoelectric cell, and when it senses enough of this light, it creates an electric current that sets off a light. Ionization type. Some aircraft use an ionization type smoke detector. The system generates an alarm signal, both horn and indicator, by detecting a change in ion density due to smoke in the cabin. The system is connected to the 28-volt DC electrical power supplied from the aircraft. Alarm output and sensor-sensitive checks are performed simply with the test switch on the control panel stays on. All smoke indications go away automatically when the smoke is gone.
Smoke detector system. The optical smoke detector consists of source LEDs, intensity monitor, photodiodes, and scatter detector photodiodes. Inside the smoke detection chamber, air flows between a source LED and a scatter detector photodiode. Usually, only a small amount of light from the LED gets to the scatter detector. If the air has smoke in it, the smoke particles reflect more light on the scatter detector. This causes an alarm signal. The intensity monitor photodiode makes sure that the source LED is on and keeps the output of the source LED constant. This configuration also finds contamination of the LED and photodiodes. A defective diode or contamination causes the detector to change to the other set of diodes. The detector sends a fault message. The smoke detector has multiple sampling ports. The fans draw air from the sampling ports through a water separator and a heater unit to the smoke detector.
Lavatory smoke detectors. Airplanes that have a capacity of 20 or more are equipped with the smoke detector system that monitors the lavatory for smoke. Smoke indications provide a warning light in the cockpit or provide a warning light or audible warning at the lavatory and at flight attendant stations that would readily detected by a flight attendant. Each lavatory must have a built-in fire extinguisher that discharges automatically. The smoke is located in the ceiling of a lavatory. Lavatory smoke detector system. If there is a smoke in the sensing chamber of the smoke detector, the alarm LED comes on. The timing circuit makes an intermittent ground. The warning horn and the lavatory call light operate intermittently. The smoke detection circuit makes a ground for the relay. The energized relay makes a ground signal for the overhead electronics unit in the central monitoring system. This interface gives these indications: lavatory master call light flashes, cabin system control panel, and cabin area control panel. Pops up window shows, and the lavatory call chime operates. Push the lavatory call reset switch or the smoke detector interrupt switch to cancel the smoke indications. If there is still smoke in the lavatory, the alarm is LED color red.
Optical smoke detectors. Detection in based on light scattering principle in normal state. IR LED emits infrared light beams. There is a barrier in optical chamber that prevents IR lights from the reaching photodiode. In case of fire, smoke particles get into optical chamber of smoke detector. RI lights coming from IR LED refracts and scatters onto the photodiode. When scattered IR lights beams reach photodiode, optical smoke detector sends fire alarm signal to fire alarm control panel. Since detection principles of optical smoke detectors is based on light scattering of particles in optical chambers, smoke detectors should not be used in places where there is vapor, dust, and exhaust fumes in order to prevent false alarm.
Detectors are one of the fundamental components of the fire detection system. They detect fire in the first second of incident and send fire alarm signal to the control panel. Detector type vary depending on which indication of fire they detect and the detection principle. Fire has three main indications: smoke, heat, and flame. Smoke detectors are classified as optical smoke detector, ionized smoke detector, and beam type of smoke detector. Optical smoke detector are the most frequently used smoke detectors. They are used in residence, hospital, hotels, shopping malls, etc. They are secret heroes who save us from devastating damage of fire.
I find smoke detectors a marvel of engineering. Let me show you how it works. This black cylinder has louvers which guide air into the detector. Now it hides the essential part of the device. Tucked in here lies about 1 microcurie of radioactive americium-241. That's about 0.29 micrograms. That tiny bit of radioactive material generates a small current that makes the detector work. Let me explain how. Air flows between these two electrodes. Now, of course, air doesn't conduct electricity, but when alpha particles from the radioactive americium slam into the oxygen and nitrogen molecules that make up air, they knock electrons about, leaving charged gas molecules. The 9-volt battery causes these ions to move, thus creating a current. Now, here it's tiny, something like 100 picoamps, about 100 billionth the current flowing in your home. When smoke enters the chamber, the ions attach to it and slow down and often lose their charge. Both events cause the current to stop, which triggers the alarm. Now, to make such a compact thing work with only a 9-volt battery required the solid-state revolution of the 1960s. Let me show you. If I remove the two electrodes, you can see a small integrated circuit. It incorporates a marvelous device called a MOSFET, which can detect those very small changes in current. In the detector, it serves as an on-off switch triggered by the tiny current between the electrodes. Like every transistor, its operation depends on being able to make diodes from semiconductors. Recall that a diode allows current to pass in only one direction because it uses two types of semiconductors, a type that uses negative charge carriers and one that uses positive charge carriers. Flip that battery and the flow of charge stops. Now, to build a MOSFET, we take two such diodes and put them together so that each is reversed. Now, this seems useless because no current will ever flow through such an arrangement, but engineers embed this diode sandwich into the same type of semiconductor as the diode ends that touch. Then they place metal contacts at the ends of the diodes and on the block of semiconducting material. Next, they coat the diodes with a thin layer of silicon dioxide. Unlike metals or semiconductors, this doesn't conduct electricity at all. On that, they place one more metal contact called the gate, which opens or closes the current channel between the source and the drain. When we create a voltage difference between the gate and the source, it generates a field through the insulating layer that draws the free positive charge carriers toward the gate, opening a channel that now allows current to flow. In a circuit, we use the 9-volt battery to generate a potential difference between the source and the gate. It biases the gate so that the current flows through the MOSFET, thus turning on the horn. So we counter that with a current flowing from the detector. Here is where the ionized gas creates the tiny current between the two electrodes I showed you earlier. That current passes through a large resistor and creates a voltage that opposes the battery, and it shuts down current flow through the MOSFET. If smoke enters the chamber, the tiny current stops, the MOSFET allows current to flow in this section of the circuit, which triggers the horn. Now, to me, this is engineering at its best. Simple, reliable, and inexpensive, and saving countless lives. I'm Bill Hammack, the Engineer Guy.